Hello everyone. Um, Today I'm going to continue this series, um, and we left off at graphs, and we will continue from there. But before I continue, wait, let me first check if stream is working right. I think yes. Yes, the stream is perfect. I'll open chat here. Fine. Give me just a minute. Fine. So before we continue, I think we should revise previous class, right? I am audible, right? Yes, I am. Okay. So, yes, documents, day one. So, what did we do? I think it's fine. Theory of computation, we saw that theory of computation has three central areas of study. That is study of automaton, study of computability theory, and study of complexity theory. And we saw that all of these different areas deal with one problem. And what is that problem? That problem is uh, to classify if a problem is solvable or not. Okay, so how do we decide if a problem is solvable or not? Um i think i think I am mistaking something. um what are the fundamental capabilities and limitations of computers? Okay, I was wrong about solvable and not solvable. It is actually what are the fundamental capabilities and limitations of a computer. To define, basically, to define the abilities of a computer, we explore all these three theories. All right. So all these three central areas help us decide what are the abilities of a computer. Um, Coming to first area, automata. We just saw that scheduling problem is NP hard, and to I basically I tried to uh, guess why it is hard, but I wasn't able to reach a conclusion for this part, and then I'm just moved on with the topic, thinking when actually understand what is NP hard, then maybe I can uh, understand why this is NP hard. Okay, so this book approaches to theory of computation in reverse order. We first study complexity theory. So what is basically complexity theory? Um, the profound question was to define the limitations and abilities of a computer. So this theory approaches that question by classifying problems as easy or hard based on their computational difficulty. All right. So you maintain, it's like you maintain a periodic table of hard problems to refer it. And if some new problem is able to refer to that problem from that kind of periodic table you made, um, then you can easily say that this new problem is also is also categorized as hard or whatever. Okay. And it also, this theory also defines some ways to approach these hard problems uh, by three ways. First way is that we can alter the problem, the part of problem which is actually making it hard. We can alter it, and maybe then it can just become easy. And we can approx the solution, or we can solve in other cases rather than worst case, because most of the problems are just hard in worst case, and all other cases it is easy to solve. Then we see computability theory. In computability theory, we just classify problems as solvable and not solvable. So the difference between complexity theory and computability theory is that we classify problems as easy or hard in first case, and in computability theory, we classify problems as solvable and not solvable. Now, coming to automotive theory, it defines and gives us properties of various mathematical models of computation, for example, finite automata, context-free grammar, etc. Mathematical models of computation. Then then actually this book dives into basic mathematics, which is sets, relations, and functions. So I just write the definitions which I thought is necessary for me. That is, like, you see, uh, a sequence is a list of object in some order. A sequence with k elements is a k tuple. A two tuple is called an ordered pair. Then different notations in which we can write a function as this, this, and this. Okay. Let the domain of a function f be cross product of many sets. That means input of f is a k tuple. We will provide a k tuple, an element from each one of these sets. Now, the definition is that a function with k arguments is called a k-array function. So basically, any function that is going to take some k tuple is a k-array function. And because it is taking k arguments, k is the arity of the function. It has to take k arguments because k is the arity of the function. If k is 1, we just classify the function as unary function, and if k is 2, we classify the function as binary function. And to represent binary function, we have two notations, that is infix notation and prefix notation. Infix notation is basically when you express a symbol between two operands. Operator is between two operands, and in prefix notation, you just write the name of function, typically like programming syntax. Okay. So now a predicate or property is a function whose range is true, whose range lies in the set of true and false. Example, even property. I think this is this is related to what mathematical reasoning and logics, because we actually study properties, right? I might be wrong. A predicate or property is a function whose range is in the set of true or false. Now, I just wrote about equivalence relation. Equivalence relation is something which follows RST. RST reflexive. It should be reflexive, it should be symmetric, and it should be transitive. And that's it for session 1. Sets, relations, and functions was over. And now we continue from graphs. So what is graph? First of all, we say about undirected graphs. Undirected graph, or simply graph, is a set of points which lines with lines connecting some of the points. The points are called nodes or vertices. An undirected graph. Okay. I'm here. I should actually first. Where is it? Save the file. Day 2. Okay. Is a set of points with lines connecting some of the points with lines connecting some of the points. The points are nodes or vertices. The lines are called edges, as shown in following figure. All right. Set of lines connecting some points. The points are nodes or vertices, and the lines are called edges. Should I make some lines? To make, actually, I need to edit it a little. Pass, customize, line tool, close. If I'm customizing, let me just do one more thing. Put it all the way here. And fine. This is easier to access. So the points are like lines. Maybe I can make anything. I don't need to define like I don't need to make it closed, completely closed. It's my choice, I think, to actually define it. So these are all the vertices. The number of edges at a particular node is the degree of that node. The number of edges The number of edges at a given node is called degree of that node. So this has a degree of 1. This is a degree of 1. This has degree of 1, 2, 3, 4. This has degree of 2, has 3. This has 1. No more than one edge is allowed between two between any two nodes. We may allow an edge from node to itself, called a self loop. No more than one edge is allowed between any two nodes. These are the two nodes, and there's only one edge between them, so fine. We may allow an edge from node to itself, called a self loop. Node to itself, self loop, depending on the situation. In the graph G that contains nodes I and J, the pair IJ, this is the ordered pair, the tuple, binary tuple, represents the edge that connects I and J. The order of I and J doesn't matter in an undirected graph. So the pairs ij and ji represent the same edge. So it is an ordered pair. Sometimes we describe note that so you also have to number the nodes. I actually wrote degrees, but instead I should let's say let's say I write I can do it like that. Node number is more important, I think, and it says me 1, 2, 3, 4, 5 represent the edges that connects I and J. So if I say 3, 2 or 2, 3, it is same thing. Sometimes we describe undirected edges with unordered pairs using set notation. The order doesn't matter in undirected graph, but if the graph is directed, the order will matter from I to J, from J to I. If V is the set of nodes of G and E, V set of nodes of G and E. What is happening today? Is my brain not braining? We say this graph, vertex and edges, right? If vertex is the set of nodes of G and E is the set of edges, okay, and now I understand. Set V, set of nodes of G. V is a set E is a set. V is a set of nodes. E is a set of edges. G is graph. V is set of nodes, nodes or vertex. Finally, E is set of edges. G equals to VE. Mathematical notation. You can write things like 1, 3, 3, 2, 3, 4, 3, 5, 4, 5, 5, 6. So the number of edges equals to number of pairs, I think. 1, 1, 2, 3, 1, 2. I can do this right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Fine. We can describe a graph with a diagram or more formally by specifying V and E. For example, a formal description of the graph in figure 0.2a is this. 1, 2, 3, 4, 5. This is V set, if I'm correct. V is a set of nodes and 1, 2, 3, 4, 5 are nodes. And then you specify all the edges. 1, 2 connects, 2, 3 connects, 3, 4 connects. Overall again, 1, it should be like 1, 2, 3, 4, 5. So you have 1, 2, 3, 4, 5. Fine. And a formal description of okay. And actually, you know what? It is possible that I will not specify this as a node, and what will that do to me is basically I see all these. I will actually count this whole segment as one edge instead of these two broken edges. Fine. Graphs formally graphs frequently are used to represent data. Nodes might be cities and edges. Nodes might be cities and edges the connecting highways, or nodes might be people and edges the friendships between them. Um, Okay. Graphs frequently are used today. Okay, fine. Sometimes for convenience, we label the nodes or edges. So for convenience, we label the nodes or edges of a graph, which then is called a labeled graph. Okay. Because 0.13 represents a labeled graph whose nodes are cities and whose edges are labeled with the dollar cost of the cheapest non-stop airfare for travel between those cities if flying non-stop between them is possible. Fine. We say that a graph G is a subgraph of graph H if nodes of G are a subset of all the nodes of H and the edges of G are the edges of H on corresponding nodes. The following figure shows a graph H and a subgraph G. This subgraph G is highlighted. Uh, okay. Graph G is shown darker, is a subgraph of graph H. So basically, na, both will be subsets. I think um, you take the V set, take a part of it. You take the E set, take a part of it, and make the complete graph. And that graph is, I think, subgraph. So what's a path? A path in a graph is a sequence of nodes connected by edges. A simple path is a path that doesn't repeat any nodes. A graph is connected if any two nodes have a path between them. A simple path is a path that doesn't repeat any nodes. Okay. A graph is connected if every two nodes have a path between them. If I understand correctly, you mean let's say let's say I make a graph like let's say I make a graph like this. Fully closed graph. So you mean to say, let's say this is 1, 2. I made it too big. 5 nodes. I can overwrite, let's say like this. I can also change color. That doesn't repeat any nodes. I can call I can call whole graph Path will be basically non-repeating nodes. Means if I come back, it won't be a path. Well, I mean simple path. It is a path, but not a simple path. Sequence of nodes connected by edges. Simple path is a path that doesn't repeat any nodes. It would be a nice problem to cover all of the edges in a way that no one is repeated. And I can't come to node number 2 with a path like that if I have to make a simple path. Because if I come, let's say, reverse, it's not a simple path anymore. If I come, let's say, like this, it's not a simple path anymore. A path in a graph G is a sequence of nodes connected by edges. A simple path is a path that does not repeat any nodes. A graph is connected if every two nodes have a path between them. Graph is connected if every two nodes have a path between them. A path is a cycle if it starts and ends in the same node. There are so many definitions. Graph is connected if every two nodes have a path between them. And now path is a cycle if it starts and ends on same node. Now a simple cycle is one that consists of at least three nodes and repeats only the first and last nodes. A graph is a tree if it A graph is a tree if it is connected and has no simple cycles. As shown in figure 0.15, a tree may contain a specially designed designated node called the root. The nodes of degree 1 in a tree other than The root are called leaves of the tree. But okay, a simple cycle is one that contains root and leaves. A directed graph has arrows instead of lines, as shown in following figure. The number of arrows pointing from a particular node is the out degree of that node, and the number of rows pointing to a particular node is called n degree. Degree is the number of edges that come in and out. In a directed graph, number of arrows pointing from a particular pointing a particular node is called n degree. In a directed graph, should I make a directed graph here? Yes. Let's say I make some nodes first. In a directed graph, we represent an edge from I to j as pair ij. The formal description of a directed graph G is VE, where V is a set of nodes and E set of edges. The formal description of graph 0.165. You just specify the direction of specify these things like in the direction like 1 2 2 1. Yes. A path in which all the arrows point in the same direction as its steps is called a directed path. A directed graph is strongly connected if a directed path connects every two nodes. Directed graphs are a handy way of depicting binary relations. If R is a binary relation whose domain is D cross D, a labeled graph G, a labeled graph G, which will be a tuple of again D and edges, represents R, where the directed graph shown in this example represents the relation given in example 0.10. Oh, I should study somewhat about no binary relations. Binary relation. In mathematics, a binary relation associates some elements of one set called the domain with some elements of one set called the domain with elements of another set, possibly the same. Oh, I just forgot. Sorry for flashbanging you guys. In mathematics, a binary relation associates some elements of one set called the domain with another set called codomain. Precisely, a binary relation over sets x and y is set of ordered pairs x and y where x is element from where x is an element from this x set and y is an element from this capital Y set. It encodes the common concept of relation. An element x is related to an element y if and only if the pair xy belongs to the ordered pairs that defines the binary relation. So what defines a binary relation? Let's say an example binary relation is the divides relation over the set of primary numbers p and a set of integers z, in which each prime P is related to an integer z that is a multiple of p, but not to an integer that is multiple of small p. Okay, I'm confused. I'm confused here. We have two sets p and z in which each prime number p, okay, uh, p is of course an element from the set of prime numbers, and z is a integer from the set of integer is a number from set of integers, element from set of integers. So now a prime p is related to a prime p. Now p is related to z that is multiple of p, but not to an integer that is not multiple of p. So p should be multiple of z. In this relation, for instance, the prime number 2 is related to numbers like 4, 0, 6, 10, because this integer is a multiple divides. So p divides 4, yes. P divides z, yes. 2 divides 4, 2 divides 0, 2 divides 6, 10, etc. But not 1 or 9. Such as the prime number 3 is related to 0, 6, and 9, but not to 4 or 13. Alright. So binary relation is a homogeneous relation when x equals to y. A heterogeneous relation when it is not necessary that x must be equal to y. Binary relations and especially homogeneous relations are used in many branches of mathematics to model a wide variety of concepts. These include, among others, greater than is equal to divides relations, is congruent to relation in geometry, it adjacent to in graph theory, orthogonal to in linear algebra. Now, function may be defined as a binary relation that meets additional constraints. Binary relations are also heavily used in computer science. So, if my understanding is correct, you just, if my understanding is correct, you just take like any set A and put a relation between them, any set P. Any element can be related with any element, and this relation basically is anything. This relation is basically anything. And overall, this thing is a binary relation because it is relating two elements after all. So we have a lot of operations on binary relations. We can represent binary relations in matrices. Okay, where was I? Binary relation. A path in which all the arrows point in the same direction. Let's say I point in here, then I point in here, point in. I mean, like, let's say if I point like this, these all arrows are pointing kind of going in same direction. But if any point comes like this, now it is not in some direction, it is reversed. So that won't be directed graph. A directed graph is strongly connected if a directed path connects every two nodes. Directed graphs are handy way of depicting binary relations. How this is related to this? If R is a binary relation whose domain is represents this relation, where this edges will be basically all the binary tuples where X is related to Y and R is the binary relation. I think this is the point I can maybe take help of artificial intelligence. Um, it says directed graphs are a handy way to represent binary relations. Can you explain that part in detail? This is one of the most important ideas in discrete mathematics and graph theory. The sentence is saying something much deeper than than it first appears. What is a binary relation? A binary relation is simply that tells us which pairs of elements are related. Let's suppose we have a set. Is a binary relation simply tells us which pairs of elements are related. Suppose we have a set, and the binary relation R is the subset of this cross product, where means every possible ordered pair. The complete Cartesian product is okay. There are 16, yes, of course, 16 possible pairs. A relation simply selects some of them. So let's say this is a relation, and this means A is related to B, D, C to A, D to D. Nothing else is related. How do we normally write it? This is mathematically as a set, we can write it like this. This is mathematically correct, but imagine having 10,000 elements. Now you will have millions of ordered pairs. Reading them becomes impossible, but representing it as a graph, instead of writing ordered pairs, we create one node for every element and one arrow for each pair. Okay, one node for each element and one arrow for each pair. So it's basically like this. You have a node, or more clearly, A to B, A to D, C, C to A. You made two graphs, every ordered pair. Every ordered pair becomes exactly one row. This is the entire idea. Why directed? Because it's not talking about strongly directed graph or what was that? Or directed path. It's just saying directed graph means a graph with direction. And that makes a lot of sense now. Of course, A is related to B, but B is not related to A. Binary relation is just a collection of ordered pairs. Nothing complicated is happening. A graph is simply a picture of a relation. Why is this useful? Imagine this relation written as these pairs, but the graph is so simple. Immediately shows who points to whom. Cycles, isolated nodes, connected components, reachability. Your brain understands a graph much faster than the list. So why does the definition use this? The graph consists of vertices and edges. The book writes this because T is a set of vertices, the same set as the relations domain. Relations domain, and E is the set of directed edges. Now look at this definition of E. Put an edge from X to Y if and only if X is related to Y. We are talking about graph theory and you read this statement as put an edge from X to Y. It makes so much sense. If and only if X is related to Y. So if A is set A is related to set B, then this, okay. A real world example would be like how people are related, okay. You can make a social media with this graph. A key insight: a binary relation is nothing more than a set of ordered pairs. And every relation is a subset of a cross product. A directed graph is nothing more than one vertex from each domain in D. One vertex one vertex for each element in D. One directed edge for each ordered pair in R. So there is one-to-one correspondence, binary relation, directed graph, element X, vertex X, pair XY, arrow XY, relation R, edge set E. We represent the relation represented with an edge. This is something I should put in here, I think. I want to color it. Yes. Binary relation, directed graph. Wow, it literally made an arrow. Edge, pair XY. Relation R. I think it was fine. Subset cross product. Hmm. Okay, we completed the graph theory basics. Now it's strings and languages. Strings of characters are fundamental building blocks in computer science. The alphabet over which strings are defined may vary with the application. For our purposes, we define an alphabet to be any non-empty finite set. String of characters are fundamental building blocks in computer science. The alphabet over which the strings are defined may vary with the application. Alphabets over strings are defined. Okay. For our purposes, we define an alphabet to be any non-empty finite set. The members of the alphabet are the symbols of the alphabet. Okay, this alphabet is a set, and this alphabet literally means what we say alphabet, a character. We generally use capital Greek letters to designate alphabets and a typewriter font for symbols from an alphabet. The following are few examples of alphabets. Designate alphabets and a type. Okay, that is fine. Alphabet is a non-empty finite set. Note that it must be finite. You can't make an infinite set of symbols. We generally represent capital Greek letters this and this to designate alphabets and a typewriter font. Okay. So example of I should write examples of alphabet sets. This is an alphabet set E1, which contains two elements, 0 and 1. This is an alphabet set which contains a lot of alphabets, let's say from A, B, C uh, to the very Z. Let's say you can use this. A string over an alphabet is finite sequence of symbols from that alphabet, usually written next to one another and not separated by commas. That's easy, right? A string over an alphabet over a set of alphabet. A string over an alphabet finite set of finite sequence. Okay. If W is a string over alphabet, the length of W written as absolute value, of course, absolute value always represents the length, the absolute length, is the number of symbols that it contains. And the string of length 0 is called empty string and is written as epsilon. The empty string plays a role of 0 in number system. If W has length n, we can write where you have basically broken the. Okay. String Z is a substring of W if Z appears consecutively within W. For example, CAD is substring of. Okay. If we have string X of length M and string Y of length N, the concatenation of X and Y will be this. Well, those are basic terms. All of this is very obvious. If you just think of the word alphabet as a set of symbols, then all of this actually makes sense. Is a string is basically a string is basically a sequence, and that sequence will have all the symbols, and those symbols must be the subset of alphabet. The lexicographic order of strings is the same as familiar dictionary order. We will occasionally use a modified lexicographic order called shortlex order, or simply a string order that is identical to lexicographic order except that the shorter strings precede longer strings. Thus, the strings ordering of all strings over the alphabet 0, 1 is like this shortlex order. Shortlex order is something to note because I think this is going to be used a lot in this book. Now, Boolean logic is a mathematical system built around the two halves, two values true and false, through though originally conceived as pure mathematics. This system is now considered to be the foundation of digital electronics and computer design. The values true and false are called Boolean values and are often represented by the values 1 and 0. We use Boolean values in situations with two possibilities, such as wire that may have high or low voltage, a proposition that may be true or false, or a question that may be answered yes or no. We can manipulate Boolean values with the Boolean operation. The simplest Boolean operation is the negation or not operation, designated with the symbol not. The negation of a Boolean value is the opposite value. We designate the conjunction or AND operation with the symbol looks like A. A means and adding, so conjunction. No, no, it's like multiplying. So conjunction is like multiplying. The conjunction of two Boolean values is 1 if both of those values are 1. The disjunction or operation is designated with the symbol V. The disjunction of two Boolean values is 1. Okay, this is fine. We use Boolean operations for combining simple statements into more complex Boolean expressions, just as we use arithmetic operations plus and multiply to construct complex arithmetic expressions. For example, if P is a Boolean value representing the truth of the statement the sun is shining, and Q represents the truth of the statement today is Monday. We may write P and Q to represent that the truth value of the statement is sun is shining and today is Monday. And similarly, the sun is shining and or today is Monday. Operands of operation. Several other Boolean operations occasionally appear. The exclusive or XOR operation is considered by this symbol and is one if either but not both of its operands is one. XOR operation is just like OR operation with just one difference that if both values are 1, both values are high pulse, both values are true, then it gives false. Just like OR, but okay. The equality operation written with the symbol double arrow is one if both of its operands have same value. Finally, the implication operation is designated by symbol forward arrow and is zero if the first operand is one and its second operand is zero. Equality operation. We can establish various relationships among these operations. In fact, we can express all Boolean values of Boolean operations in terms of and not operations, as following identities show. The two expressions in each row are equivalent. Each row expresses the operation in the left hand column in terms of operations above it. Good morning, Alok. Welcome to the stream. Now we see some identities. Yay. No, this is not discrete math actually. Matlab, it is discrete math, but I'm studying theory of computation. That might not be visible. TOC includes DM. Yes. Everything is interconnected. Yes. I'm going to college today. I have taken sannyas from college. I am might go to college on 10th. It is next week. So need to complete my pending tasks ASAP because maybe then I won't get any time. I know. I actually want to keep this channel in English because subtitles are auto-generated, and to basically have a broader audience. Oh, this is great. I'm actually seeing your messages in English. Okay. You are writing in Hindi, but I'm seeing in English. Yeah, this is something new I saw. Okay. So what are your plans for today? No, it's fine. You can write. Your last message is actually not translated on my screen. Ah, yes. Which teacher? I think there are new teachers. Foreigner. Ajnabi. Okay. Well, the teachers are Ajnabi to me as well. Did you go to college in previous 2 days? Oh, so our previous TOC teacher is actually not teaching us DAA. I thought she will be teaching us DAA. What was the full form of DAA? Wait. I think it was design algorithm something. 10 minute. Okay. Well, I think after this session, I will write a blog, and after writing my daily blog on computer networks, I will move to, yes. Okay. First day, I don't think any class happens. But actually, they have, um, I think last year college started from 19th of August, but everyone is saying last year also it was early. Okay, so we completed section 0.2. Um, okay. Okay, bye. Save environment. Yes, always save environment. My streams are eco-friendly. Bye. Okay, so section 0.3. Definitions, theorems, and proofs. Theorems and proofs are the heart and soul of mathematics, and definitions are its spirit. Just wait a minute. Theorems and proofs are heart and soul of title. Oh, okay. TOC, lol. Yes. This chapter will be completed soon, I think. There are some theorems I have to study. Well, I don't think it's soon. There are a lot of theorems, then exercises. And after exercises, I actually dive into first chapter, which is regular languages. Yay. So what are the definitions, theorems, and proofs in this section? Okay, literal definitions. Definitions describe the objects and notions that we use. What is a definition? A definition may be as simple as in the definition of a set given earlier in this chapter, or as complex as in the definition of security in a cryptographic system. So, what is precision? Precision is essential to any mathematical definition. When defining some object, we must make clear what constitutes the object and what does not. After we have defined various objects and notions, we usually make mathematical statements about them. Typically, a statement expresses that some object has certain property. A statement may or may not be true, but like a definition, it must be precise. No ambiguity that a statement is true. In mathematics, an argument must be airtight, that is, convincing in an absolute sense. In everyday life or in the law, the standard of proof is lower. A murder trial demands a proof of beyond any reasonable doubt. Demands a proof beyond any reasonable doubt. The weight of evidence may compel the jury to accept the innocence or guilt of the suspect. However, evidence plays no role in mathematical proof. A mathematician demands proof beyond any doubt. A theorem is a mathematical statement proved true. Generally, generally we reserve the use of that word for statements of special interest. Okay, occasionally we prove statements that are interesting only because they assist in the proof of another. Prove statements that are interesting only because they assist in the proof of another more significant statement. And such statements are called lemmas. Okay. Occasionally, a theorem or its proof may allow us to conclude easily that other related statements are true, and these statements are called corollaries of the theorem. Lot of great definitions. Time is passing by a lot. Uh, my general length of the stream is already bypassed. Maybe I should start earlier, or I want to continue, but so we have how many definitions there? Definitions of a theorem, corollaries, lot of things. Definitions, proof, theorem, lemmas, and okay, guys, I should actually continue the stream tomorrow. So, see ya.